All right, so section 10.6, we're going to talk about something called the standard heat of formation. So we have noticed that enthalpy change for a reaction depends on pressure, temperature, and concentration. So we haven't really seen that come into play. We've been mostly at constant pressure, and usually if we're given a temperature, it was 298 K. But these are the variables that um, enthalpy change depends on. So it's helpful to specify a standard set of conditions. So I already talked to you guys a little bit about this. So our standard conditions for enthalpy change, our standard conditions for reactions, is what we have in the lab, pretty much. So we are going to have a pressure of 1 bar or 1 atmosphere, or about the same. And our concentrations are going to be 1 molar. So 1 molar is your standard concentration. So like you've seen, standard conditions, anything measured at standard conditions has that little degree symbol, like delta H of reaction. And our standard state conditions, like I said, are pressure of 1 bar for the gases, liquids, and solids in their pure form. So we assume that they are pure. And solutions are a concentration of 1 mole per liter at a specified temperature. So most standard enthalpy values are given at that 25 degrees Celsius, 298 K temperature, but it is possible to report some at other temperatures. So you have to take a note of what the temperature is for your given standard enthalpy value. If you want to compare enthalpies, you need to compare them at the same temperature. All right, so standard heat of formation, or standard enthalpy of formation, is the enthalpy change for the formation of 1 mole. So we are forming 1 mole of a compound from the elements that make it up. So those elements are going to be in their natural form. So we're going to have our diatomic gases. We're going to have our metallic solids. We're going to have mercury is a liquid, bromine is a diatomic liquid, iodine is a diatomic solid. So you're going to have to keep in mind those natural states of the elements. So when you're looking at a standard heat of formation, it's always being formed from those elements in their natural states. And these standard heat of formation values are given with the degree symbol and the little F to stand for formation. So the delta H of formation for solid dinitrogen pentoxide is the enthalpy change when 1 mole of our compound is formed from nitrogen gas and oxygen gas, which are both our diatomic gases. So we take 1 mole of nitrogen gas plus 5/2 moles of oxygen gas, because we want to end up with 2 moles of nitrogen in our compound and 5 moles of oxygen in our compound. So the O2 is going to cancel out with the halves in our coefficient, and we're going to end up with 5 oxygen atoms in our molecule. So sometimes you're going to need fractional coefficients for these diatomic molecules because we are forming 1 mole of the species. So if we wrote instead 2N2 plus 5O2 to get 2N2O5, that is fine for our writing of balanced equations, but that is not how you would determine the heat of formation. The heat of formation has to come from making only 1 mole of the product. So we had to use 5/2 instead for our oxygen. All right, so that heat of formation for that compound is negative 43.1 kilojoules per mole, just in case you were interested. All right, some key details about our standard heat of formation values. These have units of kilojoules per mole because they are the enthalpy change for the formation of 1 mole. The delta HF value, delta H formation value for a element, for any element, is going to be 0 kilojoules per mole if it's in its elemental natural state. So bromine, like I said before, is our diatomic liquid. So when it's in its diatomic liquid form, that is its natural elemental state. So its age of formation is 0. You don't have to do anything to make it. It is found that way in nature. All right, and the last detail about these heat of formation values is that most of them are negative. So that means that the formation of most compounds from their elements in the natural states are exothermic reactions. Just happens to be that way. All right, so let's practice. So I don't know what happened when I copied that problem, but I'm going to do this one instead because I don't think there is such a thing as iodine gas with only one iodine atom. So I'm going to do this one instead, just because I feel a little better about it. So we want to write the balanced chemical equation that represents the standard heat of formation of manganese oxide. We're going to do that one instead. So manganese is one of our transition metals. So its natural state is a solid. Oxygen, its natural state is oxygen gas. So we're going to need 1/2 of a mole of oxygen gas so that our 2's will cancel out. And that will give us 1 manganese and 1 oxygen in our product. So that is pretty simple, right? That's how you do it. That's how you write the balanced chemical equation for a standard heat of formation. All right, so what can we do with those? So the standard enthalpy change for the following reaction is 342 kilojoules at 298 K. So that reaction, as given, has a delta H of positive 342 kilojoules. What is the standard heat of formation of iron chloride? So you should be able to notice that this reaction that they gave us is the decomposition of iron chloride. So if we want to form iron chloride, we have to reverse the reaction. So we have to put our reactants, we have to put our products on the reactant side and our reactants on the product side. So iron is a transition metal, so it's found as a solid. Chlorine is one of our diatomic gases, and so those are our elements in their natural state, and when they combine, they form iron chloride. So this is the reaction for the formation of iron chloride. So all we did was reverse the reaction, so we just have to change the sign on our delta H. And it becomes the delta H of formation. So the delta H of formation for iron chloride, based on this information, is negative 342 kilojoules. Like most other heats of formation, we see that it is negative. It's it's negative, which means it's an exothermic process. All right, pretty cool. All right, so Now we're going to combine the two things we just talked about today. Standard heat of formation values, when combined with Hess's law, are used to calculate a standard enthalpy of reaction. So this is our delta H of reaction, but it has our little standardized symbol, so it says standard conditions. So we're going to consider this reaction. So we're taking our sodium bicarbonate, that's what this guy is called, and we have 2 moles of sodium bicarbonate, and it's decomposing to form sodium carbonate, carbon dioxide, and water. So this reaction can be written in 4 different steps using heats of formation and reactions of formation. First, we want to take our reactant and break it down into its constituent elements. So we have sodium, hydrogen, carbon, and oxygen. So there are 2 moles, so we need 2 for all of our products as well. So there are 2 moles of sodium bicarbonate, so there are 2 moles of sodium. There are 1 mole of hydrogen gas, because there's 2 atoms of hydrogen in hydrogen gas. There are 2 moles of carbon, which is graphite, so carbon solid. And there are 3 moles of oxygen gas. So that is our breakdown of our reactant. So we broke it down into its elements. And now we're going to take our products and form our products from those elements. So if we have 2 moles of sodium metal plus 1 mole of our graphite and 3/2 moles of oxygen, that is the standard reaction for the formation of sodium carbonate. So our next one, we made our sodium carbonate and we broke down our sodium bicarbonate, so we have 2 left. So if we take 1 mole of graphite plus 1 mole of oxygen gas, we're going to end up with 1 mole of carbon dioxide. So that is the reaction for the formation of carbon dioxide from its constituent elements. And lastly, we have the formation of water from its constituent elements. 1 mole of hydrogen gas and 1/2 mole of oxygen gas. So, because these are now all written as the reaction for the formation, so 2, 3, and 4 are written the way that we expect. So those are going to have our negative enthalpy values, and those are for the formation of those 3 products. And then for our first step is actually, if you note, the reverse of a formation. So that's why it has a positive enthalpy. It is the reverse of the formation. It is the decomposition. So because we had to reverse our formation reaction, we had to use a positive sign. So you'll see this on MindTab, but for this reaction, reaction number 1, there are also 2 moles of our product. So not only did we reverse the sign, but we multiplied by 2 because there were 2 moles of our product. So the delta H of formation of this guy, our sodium bicarbonate, was actually 1/2 of, or negative 1/2 of what I have written there. So it was actually negative 951 kilojoules. You'll see that on MindTab. I took this example straight from there. So this is the delta H of formation, but to get this number that we have up here, we had to multiply it by -2. We reversed our reaction to make it not a formation, but a decomposition, and we multiply by 2 because we need to form, or we need to break down 2 moles of sodium bicarbonate instead of 1. All right. So there is another way to do this. If you have all of those reactions written out and you want to just add up your standard heats of formation to get your standard enthalpy change, which is pretty much what we did. If you want to do it in a formula form, you're going to take the sum of all of the heats of formation of your products and subtract the sum of the heats of formation of your reactants. And like we saw in the previous example, your delta H F value has to be multiplied by the stoichiometric coefficient in the balanced chemical equation. So that's why we multiplied our standard heat of formation for sodium bicarbonate by 2 and multiplied it by -2 because it was a reactant. All right, so and that's what it says down here. The sign of the delta HF values for the reactants is reversed due to the need to reverse the standard heat of formation reaction. So usually we are forming the product, but when you have a reactant that is made up of several elements, you have to reverse that and break it down into its elements so that you can cancel them out. And that's why we reverse that reaction. We need a negative sign on our delta HF. Or technically a positive sign because it's usually a negative for the heats of formation. All right, and because our heats of formation are number of moles from the balanced equation, our units are going to be kilojoules and not kilojoules per mole. So let's practice this. So we want to use the standard heats of formation that are given, so those over here, to calculate the standard enthalpy change for this reaction. All right, so our steps are to write the reactants as their constituent elements. So hydrogen gas already is, so we don't have to worry about that one. So we're going to take our carbon dioxide and we're going to break it down into its constituent elements. So we're going to have carbon or graphite and oxygen gas. This one's pretty easy. All right, so now we are going to reform our products from those elements. So we need to form carbon monoxide. That's going to be carbon, graphite, plus 1/2 mole of oxygen gas, so that we get only one oxygen atom, to form our carbon monoxide gas. Okay, and one more, our water. So we need our 1 mole of H2 gas plus another 1/2 mole of oxygen gas, so that we end up with 1 atom of oxygen. So that is the formation of water. So you can see from these reactions, when we add them together, our carbon, our graphite, is going to be a reactant and a product, so we don't need to actually worry about it. It doesn't come into our final reaction at all. Same with the oxygen. We have 1/2 an oxygen in both of these reactions and 1 full oxygen in our top reaction, so those cancel out. And we end up with CO2 plus H2 on our reactant side, which is what we had in our reaction at the top, and carbon monoxide and water on our product side. Perfect. All right, so now we just have to add up our heats of formation. So for carbon dioxide, our first step, this is not the formation reaction, this is the decomposition reaction, so we have to multiply that one by -1 because we reversed it. Carbon monoxide is a formation, so that one's fine. And same for water, that one's fine. So when we add all of these up, so we have, instead of negative 393.5, we have to reverse it and make it positive, and then we add that to our two negative heats of formation, and we end up with 41.2 kilojoules as our enthalpy change for the given reaction. All right, so it looks a little messy, but that's all that you have to do is, one, write the reactants as their constituent elements, break it down, and two, reform your products from those elements, making sure that everything that is not in your final reaction cancels out in the process. And then add up those heats of formation at the end. All right, that's it. So I'll see you guys tomorrow. All right, so moving on. Remember that we learned about bond energies back in chapter 6? So we looked at bond energy and how it was related to bond order when we were drawing our Lewis structures back in chapter 6. Now we're going to talk a little bit more about that. We can use bond energies, or bond enthalpies, as they're also called, to calculate the enthalpy change for gas phase reactions, because those bond energies were all for gas phase molecules, gas phase bonds. First, we want to assume that all of the chemical bonds are broken in the reactant molecules. Next, we want to rearrange our atoms and form products with new chemical bonds. So the first step, where we break the bonds, that is endothermic. We need to input some energy in order to break a bond. Our second step, where we form new bonds, that's exothermic. So when we write the entire enthalpy change for the reaction based on bond energies, we will say that delta H, with this little degree symbol that will be explained later, that little degree symbol means that it's at standard conditions, which doesn't matter too much right now, but it will later in this chapter and the next. Standard conditions is generally room temperature, sea level, pressure, etc. So don't need to worry about that right now, but that means, in case you're curious, so our enthalpy change at standard conditions is going to be equal to the sum of the energies of the bonds that are broken. So this is going to be positive because we're breaking bonds. So it's endothermic. And this is going to be negative. So we're subtracting the energies of the bonds that are formed. So negative enthalpy change here for forming bonds, because those are exothermic process. All right, so let's see what that looks like. We want to use the average bond enthalpy to calculate the enthalpy change for the following gas phase reaction. So our gas phase reaction is the iodine gas reacting with chlorine gas to form iodine chloride. And first, so our steps here are going to be that we want to draw our Lewis structures for our reactants and product molecules, so we know which bonds we're breaking and which bonds we're forming. So iodine gas is just two iodine atoms bonded together. And if we want to be precise with our Lewis structures, we draw all of our lone pairs on here. But the important thing is we have one I bond. All right, chlorine is going to be the same. We have chlorine gas, so we have two chlorine atoms bonded together. So we have one chlorine-chlorine bond that we're breaking. And on our product side, we're going to be making iodine chloride. And it's actually going to look the same, except with an iodine and a chloride atom instead of two of the same. And that is going to be the formation of an ICl bond. And because there are two of them being formed in our reaction, we need to multiply our enthalpy by 2 for that one. So these are our Lewis structures. So now we know what bonds we need. And I have those bond enthalpies written up here that came from our references section. So now we're just going to plug it into our formula. So our formula is delta H equals the sum of the bonds, so the energy of the bonds broken, minus the sum of the bonds formed. So when we looked those up, we found that the II bond was 151 kilojoules. That's the enthalpy of that bond. The energy that is required to break it is 151 kilojoules. Our chlorine-chlorine bond, we're going to add that because that's what our sigma tells us to do. It's a sum. So we're going to add that to the broken ClCl bond, which is 242 kilojoules of energy required to break that bond. And now we're done with our reactants, so we're going to subtract the sum of our products, our bonds formed. And there's two bonds formed from our reaction. Our balanced reaction tells us there's two formed. So that bond releases 208 kilojoules when we form that bond. So we multiply 2 by 208 kilojoules because we're making two of those bonds when we make two of those molecules. And now we just add / subtract all those numbers, and we should find that the enthalpy of this gas phase reaction, the enthalpy change, is negative 23 kilojoules. So when we form two ICl gas phase molecules, we are breaking bonds, but we are actually releasing 23 kilojoules of energy because the bonds we form are more favorable than the bonds we break. All right, so let's keep moving. So these are the steps that I just followed for that problem, and you can refer to these steps if you need some help doing these problems. So you want to draw your Lewis structures so you can find out your bonds that are broken and your product bonds that are formed. Then you want to look up those bond energies or enthalpies in your reference tables. They're in the thermochemistry reference table. Then you want to use this equation down here to calculate the enthalpy change when you plug in those bond energies from step 2 with the number of each bond from step 1. So and this is a little side note, you only have to worry about the bonds that are broken or formed. If there are any unchanged bonds based on your Lewis structure, you don't need them in your calculation.